Hello, in this video we're going to study a particular type of series and their convergence. These are called alternating series. So why are they called alternating series? Let's take a look at one of them. It's essentially any series that have something that looks a bit like this, minus 1 to the power of k. What does it mean? Like this one here, right? Let's take a look at what this one actually looks like. So the first element will be when k equals 1, so I'm going to get a minus 1 here, 1 divided by 1 minus 1. When it's 2, minus 1 I get squared, so I get a positive number, and I get plus 1/2. Subsequently, I get plus 1/2, minus 1/3, plus 1/4, minus 1/5. And you see how the sign of each element keeps alternating from negative to positive to negative to positive, and so on. So this is what an alternating series looks like. And how do we study its convergence? How do we study it? Well, first of all, for a second, let's remember how we showed that these series here diverges. How did we know? Because we used the integral test and we showed how this integral diverged and given the natural logarithm, and we showed that it diverged. So, well, okay, so this one diverges, right? Okay, great, very good, fantastic. What happens with this one? How do we determine whether this one diverges or not? Here's the test for alternating series. So what you do, you have an alternating series. I underline it because I'm not including the minus 1 to the power of k element in this thing here, because this will be minus 1 to the power of k, but sometimes it will be minus 1 to the power of k plus 1 or k minus 1 or anything really. So let's just assume that there's a series A which is alternating, okay? It's going to converge if these two conditions are met. First, the limit goes to 0, okay? Again, remember the divergence test? When if it's not 0, it diverges, otherwise we don't know. Well, if it's alternating, if it does go to 0, that's one of the things I need, okay? To check whether my series converge or not. The other thing is that any element, doesn't really matter which one, it's just not one of the first ones, just in case. Any element, next element must be smaller. Its absolute value important, must be smaller than the previous element. Okay, and let's just say that we have to show that happens with a large enough k. Now, a lot of you might think, what does it mean, large enough k? What does it mean? How do I know if it's large enough? Oh dear, you will know. Okay, and if you don't know, just if it happens that you don't know, which I really don't think it will happen, then just put a big number like 100, whatever. That will be enough. It's not very rigorous, but as I said, you're not really going to be in that situation. So that's my alternating series test. How do I use it? Great. Here's a few examples. Let's do the first one first. So again, this one here, we calculate the limit of the absolute value. Now, because it's the absolute value of minus 1 to the power of k, this minus 1 to the power of k is just going to be changing from minus 1 to plus 1 to minus 1 to plus 1. I can get rid of it. I can just write this like this. And this limit goes to 0. So the first condition is okay. Now let's calculate what happens in subsequent terms. Well, 8k is going to be 1 over k. 8k plus 1 is going to be 1 over k plus 1. Now, because it's absolute values, again, the minus 1 to the power of k disappears. Doesn't matter. And yeah, and 1 over k plus 1 is smaller than 1 over k, so the second condition's okay. You see how I didn't need to put like big numbers here? That was my point. Let's do the next one here. So this one here, k over k plus 1. First, let's do the limit of the absolute value, right? So since the absolute value, the minus 1 over k goes away, and I end up with this limit here, which is the same as this limit here, because these are always positive. And what happens here? It gives me 1. Well, here, what happens? Well, simply, it diverges. That's it. Great. Okay, moving on. So here's an interesting thing about alternating series. This is not easy to see, so sit back, stop the video if you need, go get some water, come back, because this is a little bit difficult. So once I know that alternating series converge, okay, I've already discovered that they converge. Think about the following thing. Think how the terms keep adding and subtracting, right? So I keep like, I start with minus 1, then I add 1/2, right? And then I subtract 1/3, and then I add 1/4, then I subtract 1/5. Each time I'm adding or subtracting something that's bigger or than the term that we'll go after with a different sign. And something I'm adding a subtraction to something that's smaller than the thing that was right before it. So think about like it's going to call it the truncated sum. Okay, let's suppose that I stop here. Say, okay, let's stop here. Say that maybe I'm close enough. That's good enough because 1/6. That's already starting to be small. Let's just stop here. Where do I get to? I would get to minus 47 divided by 60. Okay. Now, what happens if I do one more element? Let's see what the difference is. I'm just going to add 1/6 to this, right? Now, this point here, I'm closer. But the last thing I'm going to do here is add a number. So because I'm adding a number, I'm going to get minus 37 over 60. Now, I'm at minus 47 divided by 60. Now I'm at minus 37 divided by 60. Next time I'm going to be, again, closer to this number perhaps when I subtract 1/7. But maybe like minus 45, and then I'm going to be to minus 38, and then to, you see what I mean? Like each time I'm getting closer to the central limit. Okay, so the real limit. That's the whole point exactly. The actual sum of the series, right? The actual final sum of the infinite series, when I add all the infinite terms, the final sum is going to be a number between this one and this one. Do you agree? That's an important thing. That's the one that I needed you to think about and concentrate. Make a little drawing if you need. I'm sorry I don't have one here. I think I should have one. But think about it. Think about how the actual finite sum, the infinite sum of these series, is a number between this one and this number. Okay? Okay, now it is. So we can say that like S here, okay? S is the final sum of the series, the infinite sum of the series, minus any element, right? Minus, for example, I stop at 5. Let me stop at 5, okay? N means that I stop at 5, okay? So the final sum minus this one, well, that'd be the error, right? Wouldn't that be the error of how far I am away of the final sum if I say that it's minus 47 divided by 16? That error is smaller than taking this one and subtracting this one. So the error that I make is smaller than I take a term and I subtract the previous one. Okay? So how do I use this? What does it mean? You'll see in a minute. So the distance from a truncated sum is I stop at 5, for example, okay, to the infinite sum is smaller than the difference between the truncated sum and the next one, okay? The difference between to the 6, going to the 6th term, subtracting going to the 5th term. An important small realization here. If I go all the way to the 6th term and I subtract all the way to the 5th term, what do I end up with? I'm just going to end up with 1/6 because they're all going to cancel each other out. So this is what I'm going to be using. Let's go ahead. I have to calculate this convergence series equation between 0.0001. So the difference between the real sum and the truncated sum. This is what I'm going to be using. This is the real sum minus the particular term. It has to be smaller than a particular term, that term in particular. So for this one here, I need it to be that the real sum for truncated series to be smaller than 0.0001. So this is what I need. Now all I have to do is substitute a n plus 1 here. That's what I get. I solve the equation, so I know that if k is bigger than 9999, and I do all the series up to k bigger than 9999, I'm going to be accurate within 0.0001 decimals. Beautiful. The other one, very similar. Again, I use the same formula, 0.0001 to be smaller than this thing here. I just substituted k for k plus 1. Again, because it's absolute values, I don't really care about the minus 1 anymore, and I just have to solve this equation. Put this in your calculator, you're going to find out that k has to be bigger than 99. So that's how you use the error in truncated alternating series, this little equation here. One more thing is going to be quick, trust me. Here are some definitions that we have in series that you should know about. So it's just words and expression that your paper might use. That at this point I haven't mentioned, and I think I should because I've been talking about them in this presentation. This series here, when it's 1 over k, it has a particular name to it. This one, remember, it's divergent. It's called a harmonic series. That's it. You should know that. They might use that. Great. Another thing, if I have a convergent alternate series, okay? If I have a convergent alternate series, if I make the absolute values and the absolute values diverge, then we say it's conditionally convergent. If I take the absolute values and that converges like the alternate series converged, then we say it's absolutely convergent. Just definitions, all you needed to know. The important thing that the consequence this has is that if I have a series that's absolutely convergent, that I take the absolute values on both sides, right? And I see that converges, then the series itself converges. That's it. Important definitions to know. So here's an example. I have these two series here. Let's determine whether they're absolutely conditionally convergent. Let's start with the first one, the sine. Now, I know that the absolute value of this thing, because the sine is the value between -1 and 1, is going to be smaller than 1 over k squared plus 1, which is smaller than 1 over k squared. So it's a p series, this one here, and I know that this one converges. So by the comparison test, the sine function, this one here, converges, right? And since the absolute value converges, is it's absolutely convergent, I can say that without the absolute value converges. So that's it. That's very quick, really. I mean, you don't really have to do much. The only realizations here are to go quickly to the p series. The next one, I have this function here. So let's see what happens to this one here. I check for the series convergence. I make the limit, and the limit goes to 0. Good. I check the second condition. Here's a sub k. Here's a sub k plus 1. And I see that a sub k plus 1 is smaller than a sub k. So the series converges. The alternate series converge. Let's find out whether it converges absolutely. We have to take the absolute value. If I take the absolute value, the -1 over k goes away, and I end up with this thing here. And very quickly, if I make the limit comparison test, okay, using 1 over square root of k, which I know is a divergent p series, because p in this case here is -1/2, so it's bigger than -1, the limit is going to give me 1. So since this one is divergent, this one must also be divergent, and that concludes the example. Thank you very much for watching. Again, sorry for the long video. I'll see you next time. Goodbye.